OK. So now that we've looked at DNS over TLS and we've decided that it's a good fix, but it's not entirely what we wanted, we can go back and try to design something from scratch that does achieve all of our design goals, and that's where DNSSEC comes in. It stands for those words. It's an extension of the DNS protocol that will give us integrity on the results. So we're going to use cryptography to prove that the records are correct and that they're not tampered with. Now, an important design consideration when people were making DNSSEC is that it needs to be backwards compatible. If you think about designing DNSSEC from scratch, if we wanted to deploy it, we would have to go to every single computer in the world and tell them to stop using their old DNS code and install this new DNSSEC code. And if anyone doesn't do that, they're not going to be able to participate in DNSSEC, and getting everyone to upgrade is just going to be a giant mess. So we can't have two separate versions of DNS working at the same time. That's just going to create a bunch of headaches where people don't update their software or they can't update their software. So instead, we want to build DNSSEC as an extension. In other words, if you don't support DNSSEC, you should still be able to use regular old DNS with no problems at all. And if you do support DNSSEC, then you just do some extra stuff on top, and that gives you extra security. This is what makes it actually able to be deployed across the entire internet. So this does mean that we have to keep all of our existing design, and that's going to cause some awkward hacks, but it's something we have to work with. So we need to keep the idea of records. We have to keep the same record types. We have to keep the same idea of caching. Everything stays the same. We're just going to add some stuff on top to add cryptography and security. And once again, consequence of not designing this in from the start. So to design it, there are 5 big questions we should ask. So the first question we should ask is what cryptographic protocols we want to use. Thinking back to the cryptography unit, there are so many different protocols or algorithms that we learned about. We learned about encryption, MAX, digital signatures, public key encryption. There are all of these different cryptographic primitives. So the first thing we should do is narrow down which one we want. So you can try and predict which ones we'll think about using. So right away, I'm going to eliminate the encryption protocols, public key encryption or symmetric key encryption. We've already said we want integrity, we don't want confidentiality, so we can knock out those confidentiality schemes. They're not what we want. That leaves us with the 2 integrity schemes, MAX, our symmetric key, and signatures, our public key. Which one is better? Well, if I use MAX, I'm saying that only people with the private secret key can verify the MAC. So it's good if a small set of people with the secret key want to generate and verify MACs. But think about one of these DNS records. Is a DNS record something that's only known to a small set of people? Not really. It's something that everyone should know. It's a public piece of information. So because we want everyone to verify a DNS record and not just people with the secret key, it's a good idea to use public key digital signatures because it gives us the property that one person can sign, that's the person who owns the record, like the name server, and everybody else can verify. That's great. I want everyone to be able to verify these records because they're public. So the answer to our first question is to ensure integrity using digital signatures.